I'm Sandro Galea. I am from Columbia University in New York City. I will be speaking about thinking in systems, understanding the complex causes of population health. I will be discussing how complexity is at the heart of most population health problems and how we need to adopt complex systems methods to understand these better. Thank you very much, Andrew, for inviting me, and thank you all for coming here. Although I've been to the UK dozens of times, I've never made it to Scotland, and it's actually always been a dream of mine to come to Scotland. When I was growing up, for some reason which is not clear to me, my parents decided that we should save pennies to be able to fund a trip to Scotland, and we had an old large Methuselah of wine that was empty, and we would put all our pennies in it to saving for a trip to Scotland one day. And as you can imagine, we never saved enough pennies, so I never actually made it to Scotland as a child. So I'm very glad to be here now. So is this okay if I walk? Yes? Okay. So I am going to talk about this notion which we have been playing with quite a bit in my group in New York about systems thinking and about thinking in systems. And I developed this talk as provoked by Andrew and his invitation to try to illustrate both the thinking in systems as well as modeling in systems. And in my experience, far too frequently we tend to think of the two as separate, and I want to try to bring them together. And I want to illustrate what I mean by thinking in systems and why I think it matters. And then I want to illustrate how we can go about modeling systems. So having said that, I'm going to just plunge right in. And I want to start with population health briefly. And I want to just do a little bit of a primer into how we approach population health right now, and in particular what the role of epidemiology is in population health. And so population health starts with the notion of populations. And a lot of our thinking is around the fact that there are a certain proportion of people who are exposed, and that's the green people out of the sea of blue people. And then, of course, what happens is, although this is about population health, our typical thinking is really around disease. And so we tend to think about, let's count people with disease. Now, the reason that I run an epidemiology department, the reason there are epidemiologists is for a very simple observation that not all green people have red X's. If they all did, you wouldn't need epidemiology department. So what keeps me employed is the fact that not all the green people have red X's, and some of the blue people do have red X's. So really what we spend a lot of time doing is asking the question, how can we tell if exposure, which in this case is greenness, causes disease, causes the red X. Does this work when yeah, it does work when I do that, okay. Now, the problem that we have is that we cannot study the whole population. So what we end up doing is we end up taking a sample of this population. And when we take a sample, that causes all its own complexities, which we'll get into in a second. But then ultimately, what we do is we take this sample and we conduct analyses. So what we do is we count the unexposed without disease, unexposed with disease, exposed no disease, and exposed with disease, and come up with this 2x2 table and come up with measures of relative risk and odds ratios and things like that. And that roughly is a PhD in epidemiology, and then the rest of it is just statistical flimflammery. But the reason I'm starting with this point is I'm going to come back to this throughout my talk, but this paradigm is a paradigm that is predicated on some core assumptions that we frequently don't think about. So the assumptions, there are many, but these are just a few assumptions. So the assumption here is that we are dealing with homogeneous systems, with agents, with sort of those blue people that are roughly the same, except for factors that then we control for in statistical models. We assume really that things are not changing over time, and we assume that there is no structure. So when I showed you these models, these people here before, there's no real reason why this blue person is here and this blue person is here. So we're assuming that they're roughly interchangeable. we're assuming that there's no feedback, that there are no links between the blue person who became green, the blue person who developed a red X. And it's a very clear, deterministic, linear relationship, right? So implicit in this, and what I was showing you here, is that there's something about exposure, about greenness, that might be leading to, something about greenness that might be leading to developing a red X. So these really are the assumptions, among many, that underlie everything we do in epidemiology and implicitly in public health sciences. Now, there's good reason why we do this, in that it's actually been quite a successful model. And in many respects, over the past 50 years, we've had a lot of successes in public health. And of course, the quintessential public health success is understanding smoking. This is looking at incidence of smoking trends, and this is in Great Britain, showing smoking trends going down with the identification of smoking as a carcinogen, and then showing lung cancer roughly going down, with women's going up and then plateauing. And I'm using smoking as the illustration because when you're employed in a school of public health, I feel like it's almost de rigueur that you always mention smoking as a success. The other success that is de rigueur for us to mention, which is very apposite being in this side of the world, is Jon Snow. And we always use Jon Snow as an illustration of tremendous success, using the mythical notion of removing the pump handle from the Broad Street pump. So I want to use Jon Snow not to praise him, but to actually open up the question as to whether or not sometimes we take our successes too much for granted. So this is Jon Snow, and the question is, was this in particular a success? So the one figure that's not often shown and to our public health trainees or to epidemiology trainees is this one. So what this shows is the epidemic curve of cholera, and this shows the epidemic curve, and this is actually when the Broad Street pump was actually closed. Now, you don't need to be an infectious disease epidemiologist to conclude that that probably did not do very much to change the course of that. And I'm using this just as a touchstone to not infrequently our approach that presupposes a certain understanding of success based on our paradigms really isn't success. We have a long laundry list of interventions that are informed by our methods that have not been as successful as they should be. And I use this one. This is the paradigmatic, not successful American intervention. This is the 80s tremendous effort on just say no to drugs, which when was evaluated probably showed it actually made things worse, not better. But I'm using this only because it's evocative, but one can show many illustrations of interventions that are informed by our simple approach that ultimately do not have the effect that we think they should have. Or many observations that do not stand the test of time, which is exemplified best by this cartoon, which is, many of you will have seen this. This is Random Medical News, which says, today coffee can cause depression in twins, and another day computer terminals can cause a feeling of well-being in rats, and all that. And this is a critique that we face in epidemiology and public health all the time. One of my favorite memories of epidemiology as a discipline is that the very first professional meeting I went to in epidemiology, the very first panel I sat in on when I was a doctoral student, the title of the panel was, "Is Epidemiology Dead?" And I remember thinking, this is a great field to choose. I have a bright future in it. So the question is why? The question is why? Why is it that our dominant approach, which has been successful in many respects, fails us in other respects? Why is it that our approach is not good enough to inform these interventions, and why is it that it leads to uncertainty around causes in different contexts? And the reason in many respects is simple, which is our world is inherently complex. And that when we take that paradigm, that reductionist paradigm that I was showing at the beginning, where we have a world, some people become green, there are some red X's, we take a sampling therein, that is somehow missing important elements of complexity about how the world really works that makes it inadequate for our purposes. Now, the challenge, though, is what is adequate for our purposes? And ultimately, this is attributed to Albert Einstein, which is this notion that it is very much the way science operates, to simplify. There's nothing wrong with simplifying. The issue is that everything should be made as simple as possible, but not simpler. And the argument is that a lot of the mistakes that we make, the inferential mistakes that we make, are because we are oversimplifying, because we've taken our simplifications a step too far, and we are not thinking enough in complexity. Now, having said that, what's a complex system? There are many books on this, so this is actually my favorite summary of what a complex system is. This is the difference between a simple system, a random system. So a random system is random white and black dots. A simple system is an array of these gray squares, and a complex system is a rows. So a complex system is something that is emerging from quite complex patterns. It embeds difference in the underlying agents. It's nonlinear. It takes into account how we contact each other, takes into account the fact there's feedback and adaptation among people, takes into account randomness, stochasticity, emergence of patterns, and often no equilibrium, with changes in these systems over time. Now, when I show these, this is sort of the kind of list that one can imagine memorizing for an exam, but if you step outside of that framework for a second, you'll realize that this sort of describes the world. This is what the world is about. The world actually involves heterogeneous people, it involves feedback, it involves adaptation, it involves randomness, it involves emergence. So there is no question that the world we're trying to study ultimately is a complex system. What is the question is, what's the balance between how do we reduce the system in a way that we can understand it without taking into account the complexity, and when do we leave aside the complexity at our peril to result in false inference? Now, let me just show you a couple of tractable examples. The obvious example on this, of course, is herd immunity, and which everybody here knows about. So herd immunity is this concept about the resistance to infectious disease because we are creating an emergent property of the disease, namely immunity to the disease. So it's the notion that by immunizing enough of us, even those who are not immunized have a lower risk of acquiring an infectious disease. And that is a classic complex system issue, that you're blocking pathways for transmission, and that we as a whole have an emergent property, our immunity, that's quite different than an individual who may not be vaccinated. And that is a classic example where if you study only the individual, we would miss the emergent property of the complex system, that is the herd immunity. Now, for those of you here who are in public health, and particularly public health policy, you'll realize that this is particularly apposite for public health policy, because policy-resistant issues in public health are almost all complex systems, because people interact with one another, there is feedback, they're non-linear, they depend on history. History matters for policy. They are characterized by trade-offs, and there are counterintuitive causes and effects. Again, everything I'm saying here should be lingua franca for anybody who deals in policy. So if this is what policy is about, and these are characteristics of complex systems, it then stands to reason that we ignore some of these characteristics at our peril. Now I want to show you one figure of something which lately has been discussed a lot, which is obesity. This is from a UK group, which I chose for this talk. This is from the Foresight group. And the Foresight group has done a tremendous amount of work on mapping the causes of obesity, and this is their framework. They're talking about force of dietary habits, degree of primary appetite control, physical activity, psychological ambivalence as essentially causing our energy balance. And this is from a very nice report. And the reason I'm pointing this out is, well, that looks pretty complex to begin with, but for any of you who've actually seen the full report, you'll realize that what I'm showing you here is part of that. Right, so what I'm showing you here is the middle. And the reason I'm showing this is because I think we understand this. We're beginning to understand this, that complexity underlies these relations, these associations, these public health problems, these intractable policy-resistant public health problems that we need to do something about. And when we see something like this, it's easy to throw our hands up in the air and say, how on earth will we ever deal with it? So I suppose the point of my talk is to try to say, how do we tease this apart. And I want to show you two examples, one about how we have thought in systems, and one is how we have done modeling in systems to try to get at different aspects of these problems. And you don't need to take my word for it that this matters. This is from E.O. Wilson, who's from one of his papers, which is the greatest challenge today in all of science, is the accurate and complete description of complex systems. Now, I'm not sure it's the greatest challenge in all of science, but it certainly seems to me as an important challenge in all of science. And it also seems to me that we in public health are a little bit behind some of our peers in the other, certainly in the natural sciences, but also in the social sciences. So a lot of the work we've been doing here has been in trying to push us forward there. So let me go to the first part of my talk, which is about thinking in systems. And I want to show you an illustration from a particular paper that we just published around how thinking in systems led us to some empiric data which I think helps us conceptualize the drivers of population health in a different way. And I want to start with the quintessential English battle between Chadwick and Farr. And this is from a really nice paper by Hamlin in the American Journal of Public Health. But briefly, Chadwick and Farr had many arguments, but this particular argument was around whether or not you could actually die because of starvation in England in the 19th century. And they really had a big debate about this, largely based on what one means when one thinks about what the causes of death are. With Farr arguing that starvation could cause death, while Chadwick arguing that that didn't matter. What really mattered was the nutritional deficiency that caused death. Of course, both were right, but it was a very important debate around the time of establishing of the Public Health Act in 1848, because it informed policy directly. And I would argue that we actually have had a similar debate certainly in the United States recently, and that this is what we teach our students. So this is what all incoming public health students need to know, is that the number one killer of people in the United States is heart disease, and then followed by cancer, followed by stroke, followed by lung disease, etc. So this is what people die of. Now, in 20 years ago, Bill Foege and Mike McGuinness published this paper in over here called The Actual Causes of Death, and then in 2004 the exact same paper was essentially redone by a team from CDC. For those of you who know the story, you also know that this was controversial because of some mathematical errors, but leaving that aside, that's not the point. Mathematical errors are always the point, but it's, that's been overcome. What they did, what these papers did is they said, okay, so this is what people die of. Here's heart disease, neoplasm, etc. And they said, well, that's actually not what people die of. What people die of is tobacco. What they die of is physical inactivity. What they die from is alcohol consumption. What they die from is microbial agents. So what it was a frame shift. A frame shift from saying, what kills me is my heart disease, to saying, what kills me is my smoking. Now, at some level, that's trite. At some level, that is, that's so simplistic. But it's actually a critically important frame shift. It is a frame shift that recognizes that behaviors are causative agents in mortality, and this has been tremendously influential in American health policy in terms of helping set things like Healthy People 2010 goals and redirecting tremendous resources around these behaviors. In fact, the reason for the controversy around the mathematics in the 2004 paper is around calculation around the diet physical activity, which got a little bit messy. But this was a very small way of starting to say that our causes of death are part of a larger system of causation, that heart disease is driven by behavior, which in and of itself is nested within something larger. Now, ultimately, what they were doing is saying, look, it's not just here, but also here, that individual risk factors also matter. Now, in a commentary accompanying this paper, McGuinness and Foege say, I've lost my arrow somehow. Oh, here it is. It's also important to better capture and apply evidence about social circumstances of health status, although data are not crisp enough to quantify the contributions in the same fashion. So they recognized that these behaviors were driven as part of a larger, more complex system of foundational causes. And that if we can push the boundary of how we think of our systems from my heart disease to my smoking, we can also push the boundary from my smoking to my social networks, which influence my smoking. So this came out in 2004, and this actually became a bit of a cause for myself and our group, and we spent 7 years actually trying to deal with this point here. So we did this, and what we did is we essentially did exactly what they did in the original paper. We did a meta-analysis on social risk factors. We quantified the relative risks for the drivers of being low education, poverty, social support, area level poverty, income inequality, racial segregation. We calculated the population attributable fraction. I'm skipping the methods, we can discuss them afterwards. And we came up with this. So what we actually did at the end of the day was we quantified the causes of death that were due to low education, due to poverty, due to low social support, area level factors like poverty, income inequality, and residential segregation. Now, if you're anything like me, when you look at these numbers, you just see numbers. That's what happens to me. So I always feel like I need to ground numbers. And this grounds them a little bit. So this is what we found. And these are other causes of death based on the original paradigm. So the number of deaths in the US due to acute MI, acute myocardial infarction, is roughly the same as due to low education. The number of deaths due to stroke is roughly the same as due to low social support. Lung cancer, roughly the same as deaths due to racial segregation. Chronic lower respiratory disease, roughly the same as due to income inequality, and so on down the list. So the other thing that McGuinness and Fege did is they said they added up their causes of death. This is what they published right here. And they say, if you look down here, they say that about half the deaths that occurred in the United States were attributed to these behavioral exposures. Now, we could do the same with what we found, which actually means you end up with about a third due to social factors. I actually think that's probably problematic, and I think this multifactorial causation challenges us doing that. So why do I think this matters? Well, I think this matters because it explicitly embeds the production of health and disease within its constituent system. It says, if we can say that a certain number of thousands of us will die of heart disease, and if we can say that a certain number of thousands of us will die of smoking, certain number of thousands of us die because of poverty. And it creates a context for the system in which health is produced that elevates us beyond the simple, individual, deterministic drivers of health. From a policy point of view, it quantifies, using the exact same methods, what has been done at the level of health behavior, and it forces our hand to say, if we are going to be counting individual behaviors, we can also count these foundational social factors within a system of the production of health. That ultimately, it's not just about individual risk factors or about social relationships, it's also about living conditions and all the way up the chain to social and economic policies. So the purpose of my first illustration is that understanding that the production of health is part of a complex system pushes how we think about the production of health. And I think this is an essential task that we in population health sciences have and need to take on. Because it is a far cry from us understanding that poverty is a cause of health and a cause of disease, to a policymaker understanding that and accepting that poverty is a non-health determinant of health, so to speak, and as such needs to be part of the system that we intervene on to improve the health of the public. So that's my conceptual side. Now, I want to move to modeling. It's actually very difficult to say, I'm against social capital. It just sounds like a good thing. It's almost like It's like salt in your food. It's like, sounds like it should be bad for you. There was quite a bit of data that emerged around social capital, and this is actually one simple set of data, but from paper we did. But there are many others showing this is homicide rate up here, and this is showing different measures of social capital. And you see that as you go this way in state-level social capital, homicide rates go down. And there is a large body of literature around this, all roughly in the 90s and early 2000s, that say from this data that social capital in communities decreases violence in communities. The problem with this is that the small scale. And insofar as at the large scale it's difficult to do this notion that social capital decreases violence has been accepted in public health at face value from associations like this that equally well could be interpreted that violence decreases social capital. So why does this matter? Well, it matters because, informed by our efforts in public health, there has been quite a bit of work on social capital. This is actually, if you go on the World Bank website, you see social capital and crime, corruption, and conflict. And it actually goes on that says, right here, social capital can prevent crime and violence. And there have been interventions funded by the World Bank. And this matters if we care about that cartoon that I showed at the beginning, if we want to make sure that we're not wrong. And there have been huge efforts, including things like this is community policing in New York City. This is Bill Bratton, who was Commissioner of Health in New York City, finally winning the war against crime. Here's why. And the simple answer was these efforts of community policing around improving the community climate around notions like social capital. So the controversial question is, can this be wrong? And this has been another one of my sort of interesting peer requests, which is actually we published this paper exactly 10 years ago now. It was published in Social Science and Medicine and Dr. McIntyre, who was the editor of Social Science and Medicine, had the wisdom to publish it, I think, or she might distance herself from it at this point, we'll see. But what we did in this paper was we used the best available data at the time to ask the simple question, to say, well, we get this idea of social capital, but could it be that social capital reduces violence or that violence reduces social capital? And which one matters more? And implicit in this was that there is a complex system of social capital and violence, and the two are reciprocal. They're almost certainly reciprocal, and it's really difficult to say from the observed data that social capital causes violence, or the opposite, causes a decrease in violence, without fully understanding the reciprocal relations that underlie them, without grounding this in the complex system that it is. So in this paper, here's what we found. What we actually did is we did a series of Markov models, which it's fine, you don't need to see that. But ultimately, what it came to was we calculated, using longitudinal studies, longitudinal data from General Social Survey in the US over the period of 20 years, we calculated transition probabilities, trying to see whether there was evidence of states moving from having high social capital to their violence going down versus going from having high violence to their social capital going down. And the way to read this, because I'm going to come back to this, is actually to focusing only down here on the overall. These are different points in time, but this is what really matters. And the way to read this is to note that what you have here is these are different states, and this is a transition probability matrix saying going from state 1 to state 2. And these states, they're down here, but I've labeled them over here. State 1 is high social capital, high violence. State 2 is high and low. State 3 is low and high, and state 4 is low and low. And just to explain what's going on here, what you see here is the transition from state 1 to state 2 is high, high, goes to high-low. So what's that mean? It means if your social capital is high and your violence is high, what's going to happen is your violence is going to drop, right? And conversely, from low-low to low-high, which says if your social capital is low, your violence is going to go up. So this here would suggest that, social capital causes violence. The converse set of states suggests that violence causes social capital. So what you see here is from these probabilities is that these are lower than those ones. And what we concluded in the paper is that using this fairly crude approach, there is evidence of reciprocity, which means it's clear that while social capital is associated with some transition to lower violence, in fact, high violence is more associated with transition to lower social capital, meaning it's reciprocal, and this seems to matter more than that. Now, this approach was very limited, and there are many challenges to it. That we ultimately were using unidirectional models, and what we did is we're using Markov models to look at reciprocity by saying A leads to B, and then a separate set of models, B leads to A. We are not really taking into account dynamics, and we weren't manipulating anything to understand what's going on. Ultimately, our simple unidirectional models may be wrong, and ultimately we were burying assumptions in this model predicated on this notion of independent effects. So that was published in 2002, I think, and which means, of course, we did the work in 2001-2000, which is now more than a decade ago. And it's sort of taken us about a decade to figure out methods and to adopt methods that are now really moving into public health sciences to be able to deal with these challenges. So the fundamental question that we asked ourselves in the 2002 paper is violence lead to social capital more than social capital leads to violence? And what we've wanted to do since, and what we've now done, is to say, is this the case when we more properly account for the dynamics of the complex system that underlies the relationship between violence and social capital? And just as importantly, if that's the case, why? Why is it that violence goes to social capital or social capital goes to violence? So here's been our approach. So our approach has been using something which has gained traction in public health sciences, but really we're much more ahead of us are other fields, and certainly natural sciences, but even things like sociology and political science. And this agent-based modeling approach is essentially a way to create in silico communities to be able to manipulate and create systems that we can use to test elements of causation. So what we're doing is you have a series of agents, which are essentially electrons, little people, and that you create them within a system that you can manipulate that mimics what a social system looks like. So underlying this is this model. So this is a model that shows you here the social capital at the neighborhood level, which is associated with individual violence victimization. That's associated with neighborhood levels of violence, which influences how you rate your social capital, which contributes to your neighborhood social capital. This is also influenced by how long you are in a neighborhood, meaning that if there's violence, you're likely to leave, and if you're moving a lot, you're not likely to report much social capital about your neighborhood. And this is the core of the model. Just like the foresight model, I showed you the core first and I expanded it. I'm just showing you the core here. But fundamentally what we're doing is we are creating a system that represents the dynamics that we know exist. And I want you to note a couple of things. So if you note here, this model is explicitly cyclic. So what do I mean by cyclic? If you follow from here, you see you can go down this arrow, up this arrow, across this arrow. You see you're actually forming a full circle. This is in direct difference from the directed acyclic graphs that have dominated population health science counterfactual thinking in the past decade. So DAGs, which really are the logic models of epidemiology and public health, are explicitly acyclic. They explicitly exclude such opportunities for dynamics and such opportunity for cyclicity and feedback. So in doing this, you are creating that opportunity, and you are creating a model that we can then manipulate. So part of the point here is that, as opposed to the 2002 paper that we published, where all we could do was to say, here's the data, here's what the data shows, it's as good as we can do, and we have to accept it that way. Here, we can actually manipulate the system by meddling with pieces of it to be able to see what happens when we manipulate the complex system. So how does this work? So the way it works is we actually use real data to parameterize the system. So we used this number of studies. And what you essentially do is you're creating this system. Just to give you a sense of the data, this is social capital data, which came from a study called the New York Social Environment Study that we did in New York City. For those of you who don't know, this is New York City. My office is somewhere over there, which is roughly medium-level social capital, although within Columbia, social capital is actually down there. This is a picture of New York. Then you have the homicides in New York, again, comes from actual data. This is household income in New York. I'm just giving you maps just to give you a sense that this is real data that's going into creating this model. Once you have this data set, you can run typical descriptives as we're doing, as I'm showing you here. You can also run the same cross-sectional analysis as I showed you before. See this? Social capital score goes up, violence goes down. So this is a cross-sectional run from the agent-based model we created, showing that social capital causes a decrease in violence, right? Well, it's not showing that at all. What it's showing is that social capital and violence are inversely correlated, but this is essentially the state of literature. Literature shows this and says social capital causes a decrease in violence. You can even get fancier. We can run regression models. So this is a regression model showing social capital, various control variables. And if you just look at here for a second, you see this? You have a p-value. So that's all I want to show you here. So in this data set, we've replicated that social capital is associated with violence in a fully adjusted model. So this here, I could publish that, and that would be essentially replicating what there are dozens of papers of in literature that say, well, social capital increase causes a decrease in violence. That's exactly what we're showing here. But of course, we are doing that now statically. And what I want to do is figure out how to manipulate a system so we can understand what happens in the system dynamically. So the model works as follows. We have a set of neighborhoods. We have a set of agents. I'm using the word agent because the word people is misleading, since these are not people. This is a simulation, right? So we have to be careful. But nonetheless, if you like, you can say people. There's no men and women. This is a gender-free universe. Everybody gets along great in this universe. There are model runs over 30 steps, which is about the 30 years in the original social science and medicine paper. And let me just show you a little bit how it works. So one of the advantages of this model is, remember I said at the beginning that one of the characteristic features of a complex system is that space matters, is that spatial relations matter. So here we have space. So we have spatial, explicit space where the agents are moving around in their space. So in this case, there are 16 neighborhoods. We start off with agents assigned to neighborhoods. Those are all the agents. And if you look at these colors here, the dark color is poor. You see it down here, under 20,000. The light color is rich, people with more than 8,000. I'm going to come back to that in a second. But initially, we start with the agents being randomly assigned to the space. And the agents and neighborhoods have characteristics. So the agents have incomes. They have perceived social capital. They live in a neighborhood for a certain length of time. They experience violence. They have a history of violence. And they react differently to violence depending on their history of violence. The neighborhoods have characteristics, and the characteristics of the neighborhoods are aggregated from the individuals. So in contrast with the social capital and violence ecologic literature, we are here not imposing ecologic values of social capital and violence on these units. They are being constructed from the agent characteristics. And as the agents move around, the neighborhood characteristics also change. So let me show you an example of that. This is just illustrative. These are different colors. 1 is low and 5 is high. This is of nothing. But what you're actually seeing here is that We are aggregating averages, and essentially these neighborhoods become low and high social capital. High is light and dark is low, based on the aggregate of the agents within the neighborhood. So if the agents move around, you can see how the neighborhood characteristics move around, giving us this dynamic that is underlying these systems. Okay. And at every step in time, we have violence. Every step in time, each agent has a risk of experiencing violence based on its income, past history of violence, neighborhood income, social capital, and neighborhood violence. So, just to give you a sense of that, some agents experience violence assault. So this is again the same paradigm before. The darker agents are the poorer agents. The red become exposed to violence. So what you see is that there is exposure to violence of some agents over time, and that's based on their income level, past history, different neighborhood type, and social capital. And that is then aggregated to create neighborhood violence. So you see how the neighborhood social capital and the neighborhood violence levels that I showed you were cross-sectionally associated in that inverse relationship, that famous inverse relationship. You can recreate it, but underlying it, we now have the agents from where the social capital and violence emerge. So that's the fundamental difference with this approach versus the approach we had done before, is that now we have the underlying properties that we can manipulate that create this aggregate, which we didn't have before. And then there are rules why agents move, and these rules are all based on the literature. Agents move based on whether or not you've experienced violence, on your income, how long you've been in the neighborhood. So essentially, you move to a place where you can afford, and you move where there is lower violence. And there is abundant literature that suggests that that's actually true of human behavior. So just to give you a sense of that, again, this goes back to the poor and rich agents, with some of them exposed to violence. And what you see here is that some agents, these are the light yellow ones, are planning to move, and they move. And at each time step, some agents will move and shift. And then the violence levels also shift. And as you see here, most agents will move to low violence neighborhood. Now, if you let this model like this run unperturbed, you recreate something which has been known particularly in sociology since the 50s, which is a very clear pattern of spatial clustering and segregation. I'm not getting into race in this presentation, but there's an element here of race which actually gets very interesting. But this is well demonstrated by Schilling in the 50s, that in social structures, if left to their own devices, will result in clustering, with the poor and the disadvantaged clustering together, and the rich and the advantaged clustering together. And you can replicate that with this model. So just to show you this, again, remember the dark dots are the poor, the light dots are the rich, and the red is exposure to violence. I'm just going to run this forward in time for a second. So everybody see that? So now what you have is, you end up with, see over here? You end up with these neighborhoods which there are poor and high violence neighborhoods, right? And you see this rich, low violence neighborhood. So when you run these models unperturbed, you get this classic spatial residential segregation pattern, which is well documented in literature, so it's reassuring that the model is doing that. Okay, so ultimately, the model rules that matter here are the relationship between social capital and violence, where the agent is assessing social capital as low if he is a victim of violence, or if they're moving to a new neighborhood, and conversely, social capital is increasing if the violence is low and the longer you are in a neighborhood. So I'm going to show you now a set of results. I'm going to show you the average level of violence and social capital over time, and I'm going to show you these transitions between states of social capital and states of violence, anchored back to the original social science and medicine paper. So what I'm going to do now is I'm going to take the original paper that was published 10 years ago. I am using that as an anchor based on the empiric data, using a model informed by the empiric data behind it to try to manipulate the model to understand what was going on and what we saw in the original paper. So to peel apart the layers of the complex systems onion, so to speak. So in the original paper in 2002, we modeled what we saw, but it was very difficult to understand what was driving it. So the question is now, can we use this technique to understand the complex system better? So this goes back, this is what you saw before. This is in the published paper. Remember these numbers, 16 and 5 and 32, 32, showing that violence drives social capital more than social capital drives violence. So this is exactly what I showed you before. So I'm just showing you this just as a reference, and I'm going to come back to it. So then I'm going to run 3 experiments. We're going to run 3 different experiments. The first experiment, first model, is I'm implementing the full complex system model, but I am not putting in movement. I'm not allowing any of the agents to move. And the reason I'm doing that is because in the observational data, there certainly is no movement that we're allowing in our agents. And movement is this extra part of the system that nobody's really accounted for. So I want to see what happens to the system without movement being in it. So we run the model, and these runs look like this. This is time on the x-axis. And what you actually have here is percent of agents exposed to either violence or social capital. So you see this blue line? This is social capital rating over time. And this red line is violence over time. And this black line is cumulative exposure to violence. So the black line is always going up, because anything cumulative over time is always going up, right? But if you look here, you see how this is going down as that's going up? Everybody see that? That is essentially the dynamic manifestation of dozens of cross-sectional papers showing social capital down, violence up, right? So a cross-sectional paper that documents this shows one goes up, one goes down. That's what all those correlations and best fit lines through them show. What the cross-sectional papers are not able to tell us is what's the dynamic between that line and this line over time. And that's what we're trying to get at here. Okay, so that's the point. Now, so here's model 1. So this is the original paper. This is now the transition matrix in the first set of models as put side by side with the original paper. Notice here, so you have here this strong support for violence driving social capital, as we had in the original observational paper. But we have more support for social capital causing violence in the blue than we had in the data-driven paper. Everybody see that? These numbers here are quite a bit higher than those numbers there. And there's more support than we expected for high social capital, high violence, dropping to low social capital, low violence, and this here is lower than we expected. So in a model where we have no mobility, we're still seeing this evidence that violence drives social capital, but we have unexpectedly strong social capital driving violence relations. So we now move to the second model, where now we put in mobility. So now we're putting in mobility. We're using these data sets that I talked about before to parameterize. And now here's what the second model looks like. So again, this is the cumulative exposure to violence. And notice here again, this is social capital going down as violence goes up, and you can see it throughout the course. You're seeing more or less the same thing. Comparing model 1 and model 2, this is model 1, this is model 2. As we add mobility, you have more agent exposure to violence. Now, hopefully, the way I think it makes sense with these models is as you start seeing observations like this, is one needs to pause and say, well, why is that? Why is it as I add mobility, I'm having more of this exposure to violence? And the reason is, as you're adding mobility, if you think back to my spatial residential segregation that I showed you when I ran through time, what's happening here is you have the poor segregating in these higher violence neighborhoods, and they're experiencing more violence in aggregate. So that's why now, as you add mobility, you're starting to see a dynamic property emerge, which before we could not see. And now we're comparing transitions again. So goes back to the empiric social science and medicine transitions, and these are transition probabilities in this model. We still have, again, violence leading to social capital. There is still more support than expected for social capital leading to violence. And just to focus on the purple, there is less here than expected, where the high social capital, low violence leads to low social capital, low violence, but it's more than model 1. So this is the most notable difference between the two, this versus this. So why is it that in this model, we have these neighborhoods where the social capital is essentially dropping by itself? Notice these are low violence neighborhoods, and they're going from high social capital to low social capital, more than the empiric data which suggests we should be seeing. So what's going on? Well, what's going on is this. So if you look at these neighborhoods, and the dark green here is high, high, and the light green is high and low, focus on these ones. These are the high-low. This has high social capital, low violence neighborhoods. Those are the neighborhoods which are becoming low social capital, low violence. So really, something is happening over here. Now, the advantage of these models is that when you start seeing observations like this, where I can say something is happening because we've added mobility, something is happening to our social capital values is dropping, we can take the model apart and say, well, what could potentially be causing it? The difference here is that we've added this duration of residence. And in model 1, the agents were not moving. In model 2, the agents were moving. So something is driving this. So it could be that duration of residence is centrally important to driving social capital. Then we go back to the published literature. In fact, the published literature shows that mobility is important for driving social capital, but it's not centrally important. The other explanation could be that this here is weak. And if this is weak, it would explain why it is that we are seeing this drop in social capital even when the violence is low, and that ultimately would tell us that we're overstating how much social capital drives violence in our current model. Which then leads to the final model, model 3, where now we are tweaking the social capital violence relationship to fully empiricize the model and to come back full circle to saying, how does this replicate what we saw in the original social science and medicine paper? So now, back to this model. There's the cumulative violence, that's decreasing social capital, increasing violence. These are comparing the 3 models now. That's model 1, model 2, model 3. So now our violence level is somewhere in the middle. I'll skip that. And going back to comparing our transition probabilities, that's the empiric data, this is the model data. What you see here is, again, violence leading social capital remains strong, social capital leading to violence is low, and this probability here is now quite similar to what we saw in the empiric data. Which means that we came back to the empiric data once we fully took into account mobility, and once we realized that the social capital driving violence effect is actually lower than we had initially thought using the underlying baseline deterministic parameterization that we had in this model. So this goes back then to the question we set out to answer. So is violence lead to social capital more likely social capital to violence, and why? Well, the answer is yes. And importantly, the dynamic complex systems approach allows us to say why that is. And the key drivers are a central role for mobility, which was impossible to see without constructing a dynamic model. That violence is driving residential mobility, which in turn is driving this decrease in social capital. That is consistent with how we understand human processes. It's consistent with the observational data, but it tells us that this dynamic relationship where social capital goes to violence, violence goes to social capital, is probably more tilted in the violence-social capital relation, which can hopefully help us avoid the fate of the cartoon with the spurious observations that we're hanging our hat too much on. So I want to conclude. So this is, I try to, in dividing the talk into 2, make the point for the centrality of systems in population health and how we need to think in systems to be able to understand the foundational drivers of population health and to understand how they work. And that ultimately, these dynamic models allow us to understand complex phenomena better. And I use this example specifically to show how, while this is using in silico experiments, ultimately what we're doing is we're trying to tie this as much as possible to empiric data to narrow down our possible explanations. And in the first half of the talk, how by opening ourselves to understanding how the causation of population health is nested within these systems, it leads us to ask questions in different ways and come up with answers to the questions asked differently. So I want to conclude with my favorite quote on this. This is, one of them is that the art of research is ultimately sensitivity to decide when a useful and necessary simplification has become an obfuscating simplification. And this is actually, I think saying that this is an art is critical. Nothing that I said here today should be construed as saying that our typical paradigm should be thrown away. Remember, I started off by explaining how I see we do population health science, how we do epidemiology right now. And I'm certainly planning on continuing to give PhDs in those first 5 slides for the next foreseeable future. So my talk is not intended to say that's all wrong. Quite the contrary. The question is, when is that sufficient? And when is that not sufficient? And I try to use 2 examples, one of them of thinking in systems, to illustrate what I think is it is insufficient to say we can quantify number of smoking deaths. It is insufficient to do that and to stop there and not to recognize the foundational drivers of smoking, and that's also quantifiable. And comparably, it is insufficient to say that social capital drives violence because of the data limitations that leads us to that conclusion, and we need to figure out ways to get at that in a bit more of an intelligent manner. And ultimately, from George Box, is all models are wrong and some are useful. I like concluding with this because hopefully it wipes out the first 5 questions that say, well, your model is wrong. But apart from the defensive posture, I think there's a very interesting set of discussions about the amount of wrongness in everything I've shown you, and God knows I know what's wrong better than anybody else. The question, though, is how do we derive usefulness from our approaches? And what I'm trying to do is I'm trying to prod us to think in systems, sometimes model in systems, to get more usefulness at the ultimately fundamental purpose, as I see it, of population health science, which is to illuminate the drivers of population health so that we may do something about it. I will stop there. There's a lot of people to acknowledge behind this work, a lot of different funders, and I look forward to our discussion. Thank you.